Imagine a future where humanity expands beyond Earth to build homes on Mars, the red planet. This ambitious vision is rapidly becoming a reality, driven by groundbreaking research that utilizes bacteria to construct durable habitats directly on Mars, revolutionizing space colonization efforts. The innovative concept of building houses on Mars using bacteria embodies in situ resource utilization, or ISRU, which allows for a sustainable human presence by transforming local Martian materials into usable construction resources, rather than relying on costly shipments from Earth. On December 2, 2025, researchers from the Polytechnic University of Milan published their findings in the journal Frontiers, proposing the use of biomineralization, a process where microorganisms produce minerals to create strong construction materials right on the Martian surface. This bacterial approach tackles the enormous costs and logistical challenges of spaceflight, especially since transporting entire habitats and heavy tools from Earth for NASA's planned crewed Mars missions in the 2030s would be prohibitively expensive and inefficient. Mars shares notable similarities with Earth, such as a thin atmosphere and geological evidence of ancient water flows, making its regolith, the loose, abundant rocks and dust blanketing the surface, an ideal primary resource for on-site construction projects. At the heart of this study is a co-culture system featuring two specialized bacteria, Sporosarcina pasteurei, known for its mineral-producing abilities, and Crucoccytiopsis, a resilient extremophile, which collaborate to transform Martian soil into viable building material. Sporosarcina pasteurei secretes natural polymers that trigger mineral growth around regolith particles, effectively binding the loose Martian dust into a robust, concrete-like material suitable for structural use when properly mixed and activated. Remarkably, this bacterial mixture can act as feedstock for advanced 3D printing technologies on Mars, empowering astronauts to precisely fabricate complex habitats and structures on-site, adapting to the planet's unique terrain and needs. Crucoccytiopsis enhances the system by generating oxygen through photosynthesis-like processes, which not only strengthens the habitat's material integrity, but also contributes essential support to astronauts' life support systems in the oxygen-scarce environment. Furthermore, ammonia, a key metabolic byproduct from Sporosarcina pasteurei, offers exciting potential for creating closed-loop agricultural systems, providing nutrients for growing food crops in Martian greenhouses or controlled environments. Over time, this technology could play a role in ambitious long-term terraforming efforts, gradually altering Mars' atmosphere and soil to make it more habitable for future generations of explorers and settlers. As the researchers themselves emphasize in their study, harnessing local materials is the key to unlocking sustainable human presence on Mars, highlighting the transformative power of this microbial innovation. This clever microbial partnership overcomes the formidable construction challenges posed by Mars' extreme environment, including average temperatures of -80 degrees Fahrenheit, a thin carbon dioxide atmosphere, and intense radiation levels that degrade traditional materials. Positioned about 140 million miles from Earth on average, Mars features regolith with particle sizes ranging from 0.001 to 2 millimeters, perfectly suited for bacterial processing into stable building blocks. NASA's missions, including the Perseverance rover active since 2021, have confirmed vast water ice reserves at Mars' poles, equivalent in volume to Lake Superior, providing another critical resource for mixing with regolith in construction. This bioengineered solution, as detailed in the article by freelance journalist Julian Dossett, could render Mars settlement feasible by 2050 or even sooner, aligning seamlessly with forward-thinking visions from pioneers like Elon Musk. The prospect of a sustainable human presence on Mars has evolved from mere science fiction into a tangible, achievable goal, thanks to innovations like bacterial construction that bring us closer to multiplanetary life.